Hi everyone. So today we're just going to go through some of these example calculations that are in your notes. I'm going to talk you through how the kind of maths works for each one. There are three different types. Two of them are quite straightforward. The middle one is a wee bit tricky, but hopefully once you've seen where the maths comes from, you'll understand how to do it. And also the middle one from initial conditions is really, really rare because it is quite difficult if you don't have a really easy example. So we'll work through these. I'm going to try really, really hard not to tap my pen extremely hard against the screen and annoy everybody's ears. But if I do, I'm sorry in advance because, yeah, you all know the story. I don't have an iPad and I'm no better about it at all. So, first example is calculating concentration from K. So we discussed what K is last day. It's our equilibrium kind of expression for how this reaction is proceeding. Is it lying towards the left at the reactant side or is it lying towards the right? So what we could be asked is, given K, can we calculate the concentration of either our products or reactants? So the question is asking us for the concentration of HF, and it's telling us that H2 and F2 both have a concentration of 0.05 moles per litre. So what we need to do first of all is write our kind of equilibrium expression for this. So K equals, we've got 2 moles of HF, it's our product, so it goes on the top, squared, divided by H2 multiplied by F2. They don't have a power because there are only 1 mole of each in the equation. Now what we do is we just substitute in the values that we know. So we know that K is 45. We don't know what HF is, that's what we're trying to calculate. But we do know that H2 and F2 both have a concentration of 0.05. Now, people are probably going to do this a wee bit differently, and that's fine, but I would first of all make that a nice number at the bottom. So if you multiply 0.05 and 0.05 in your calculator, you get 2.5 times 10 to the minus 3. So what I'm going to do is I'm going to take that over to the other side. So I'm going to take it over here. If it's a divide on this side, it's going to become a multiply. So 45 times by, now remember 2.5 times 10 to the negative 3 is just the answer of this multiplication of the 0.05 and 0.05. And that is equal to HF squared. So we are trying to get HF on its own, and that's how I would tackle that first part of this question. Now, this next part, we're having to say to ourselves, we have a squared on one side and we don't want it there. The easiest way to do that is just to square root both sides. So if we square root this side and square root this side, we end up with HF equals, and whatever the square root of that number is, now it ends up being 0.1125. So all you do is type into your calculator, if you've forgotten, if you've not done maths in a wee while, the square root function, and then put 0.1125 into your calculator, and you end up with 0.34. So that means that HF, concentration of, is equal to 0.34, and that is moles per litre. And that's how we do the first one. So the first one isn't really that complicated. The only bit of that you maybe need reminded of is probably getting rid of the squared and using the square roots, just if your math is a wee bit rusty. But other than that, it's very, very kind of simple algebra, jumping things over from one side of the reaction to the other. So hopefully we don't have too many issues with that. The next one is the tricky one. Now, this time we need to use initial conditions to kind of figure this out. So, let me talk you through what that means. I've kind of called it the ICE method. Now, when I was looking this up, I found that online and I actually found it to be really useful for remembering what to do because ICE, ICE, talks you through the steps that you need. So, The question is, if 0.2 moles of H2 and 0.2 moles of F2 react in a 1 litre vessel, what are the concentrations of all three at equilibrium? So again, we're trying to find out here the concentration of HF. Okay, we're trying to find out the concentration of HF at equilibrium though, and we're told that 0.2 moles of H2 and 0.2 moles of F2 react together. So that's why we can't actually figure this out using the method before. We need to use a new method. And it's called ICE for a reason. I stands for initial. So I is initial. C stands for change. So you've got the initial conditions, whatever you're changing, and then that means at equilibrium, what are our values going to be? And what we're going to do is we're going to go through each of the examples and think, okay, at the start of this reaction, so that's our initial value, what is the value, the number of moles for each reactant and product? Well, we're told we have 0.2 moles of both reactants, so we can put those in. At the start of the reaction, we don't have any moles of product produced, so that's going to be a 0. Now, here's where it gets a bit complicated. The change we don't really know, so we give it a value which is x. Okay? So the change is if this reaction is proceeding. Now, everybody in this audience hopefully knows that as a reaction proceeds, we're going to lose reactants and form products. So what we're trying to do here is assign that a value of x that makes sense. So for the first reactant, we're going to have minus x moles because we're definitely going to be losing some amount of moles of each reactant. So we give both reactants a value of negative x. Okay, we're taking away the reactants. Why is it only 1x? Well, we need a number of moles and both of these have a number of 1. So if you're following this along, you might have been able to figure the next bit out already. If we started with 0 products, but our change, so as the reaction continues, we're going to be producing some number of moles that is x of products. If we have a 1 to 2 ratio here, you can see we've got 1 of each reactant, but 2 of the products, then we're going to be making 2 moles. So we're going to have plus 2x. Hopefully you're still with me. I know that wee bit is a wee bit hard to visualise, but hopefully I've explained it somewhat usefully. The third bit is the easy bit. All we're doing is looking at the change between I and C. So we've got 0.2 take away x for each of the reactions. And our product is just plus 2x, which is just 2x. Okay, these values, the ones that we have just written, are the ones that we want to use because we weren't given any information about equilibrium, but we've just managed to deduce that information by ourselves using the letter x. So again, some of you might be able to have kind of figured out where this is going. We're going to use the equilibrium expression, but substitute in our values at equilibrium. So we're going to be using, again, a bit of algebra. And at the end of this, we want to figure out what x is. Now, x is going to then help us get the concentration of each of these at equilibrium. So let's go on to the next bit. K was 45. 45 is equal to, if we just use the equilibrium expression from before, it's exactly the same. We're still using this. Nothing has changed. But this time we're inputting the values that we have calculated at equilibrium. So we're going to have 2x squared on the top divided by 0.2 take away x, 0.2 take away x. Okay, we can shorten this down to 45 equals, we've got 4x squared divided by 0.2 take away x squared. So we're just using the kind of laws of algebra to try and help us figure this out. So just like we did before, we don't really want a division on the bottom, so we're going to take this up here and multiply. Now this time we're going to have 45, and then our 0.2 take away x squared equals 4x squared. The easiest way, I think, to do this anyway is just to square root it right now, because that makes the numbers a wee bit easier to deal with before kind of multiplying out the brackets. So that's what I would do. You would probably get the same answer if you didn't do it this way, but that's just the way that I find the easiest. So if we square root 4x squared, then we're just going to have 4x. If we square root 45, you get 6.7, and then we're going to have 0.2 take away x. So we're getting rid of that squared, and we're square rooting this number. Now we can multiply out the brackets, so multiply these two together, multiply these two together. And if you do 6.7 times 0.2, you get 1.34. Then we're going to have take away 6.7x, and that is equal to 4x. Now from maths, again, a rule that we know, we want all of the x's on one side and all of the kind of whole numbers on the other. So we'll have 1.34 equals, now if this is a minus on this side, it's going to become a plus. So we're going to have 10.7x. If we want to get x on its own, running out of space here, we need to do 1.34 divided by 10.7. And that equals 0.13. Now, we, remember, have just calculated the value of x. That's not what we want. We want the concentrations of the three different reactants. So, if we go back to our kind of ICE table, we can see that at equilibrium, the concentration of H2, for example, was 0.2 moles minus x. So if we're taking away this x value, this 0.13, then for H2, where can I write this? I'm just going to write it over at the side. So H2 equals 0.02 take away 0.13, and that gives us 0.07 moles. We have a litre vessel, so that means the concentration is 0.07 moles per litre. The exact same is true for the other reactant, which was F2. We'd have 0.02 take away x. Now we know that x is 0.13. That's the exact same sum, so we end up also with 0.07 moles per litre. The only difference is when we are trying to calculate the concentration of HF, our value for that was 2x. So what we have for the concentration is 2 times x, which is 0.13, and that gives you 0.26 moles per litre. Again, we're in a 1 litre vessel, so whatever the number of moles we have, we can turn into concentration in moles per litre. So yes, I do know that that is quite a big kind of sum to do, but you need to know how to do that. I did try and come up with an example of that one for you to try, but the actual mechanics of trying to get one that works out, not too complicated that it doesn't work, was really, really difficult. So just try that one again by yourself. Make sure you can go through all the steps. I'll have a wee go at it again, but for right now, we're moving on to the third type. So example 3 is calculating K, this time from concentration. So this is really just the reverse of example 1. So again, what we're going to need to do for this is to write out the expression for the equilibrium constant. But this time we're going to substitute in all of the concentrations. So this actually makes it a wee bit easier. So HF was squared, so we've got 5 times 10 to the minus 2 squared divided by 1 times 10 to the minus 3 times 1.5 to the minus 3. All you have to do is bung all that in your calculator and see what you get. I'll take a wee kind of step first. 2.5 times 10 to the negative 3 you should get for the top line, divided by 1.5 times 10 to the minus 6. That does make sense. If you pop that into your calculator, you should get 1666.6. Remember, K has no units. There are there's two practice questions for you to try. Go ahead and try these just now, and what I'll do is I will just post the answers for you to check and make sure you've done them correctly. Thank you for watching this. Hopefully see you tomorrow, and have a nice day. Bye.